and their application is the topic. And I'm going to present this in 3 steps. There are 3 segments of my talk. We'll begin with the importance of satellite meteorology, particularly to the South Asian region. We'll see how the satellite image can be interpreted. After that, we'll see how products can be derived from satellite data. We'll assess the contribution that satellites have made to weather prediction, application to climate studies, and I'll wind up this talk in a futuristic note. You're all familiar with the geography of South Asia. It's a unique place, and I think it's the geography of extremes. We have some of the tallest mountains of the world in our region. We have the wettest places on earth in our region. We have 2 plateaus, one to the north and one to the south. We have glaciers, deserts, forests, fertile plains, river systems, oceans, and islands. I think you just name it and we have it. This is the geography of extremes of South Asia in which we live. It's difficult even to understand the climate of South Asia. It's extremely complex. And we have, because in fact, South Asia is called the land of the monsoons. It brings in heavy rainfall, landslides, floods, and droughts. There are 2 oceans around us. So we have tropical cyclones with their storm surges. There are low pressure systems which move across South Asia from west to east, bringing snowfall and cold waves. We have a desert that results in heat waves and dust storms. And of course, there are local systems like thunderstorms. We are not only finding it difficult to understand the present climate, we are also disturbed by the future worries because we are worried because of climate change if the monsoons will not be as good as they are now, whether the intensity of tropical cyclones will increase in future, whether the number will increase, whether we'll have more heat waves coming in, and so on. So all of these things result in something like somewhere to go to find out the answers. And one place where we can go to find out that answers is satellite meteorology. South Asia is actually a very highly populated region of the world. But paradoxically, there are places where you cannot live. And there are many places where you cannot reach. And there are places of dangerous weather where you can't even enter. And yet, we are required to get observations from these places if you want to understand the climate of South Asia. Satellites give us that information. Satellite meteorology, I'll say, is a relatively new science. It's something like 60 years old. Very new compared to conventional or classical meteorology. And that is because satellite meteorology is a technology-driven science. That technology was the ability to put an artificial satellite in space, which we attained sometime in the 1960s or a little before that. And the first weather satellite was launched by the US on 1st April 1960. The name was TIROS-1. The acronym TIROS had the letter T, and T stood for television. Because this first weather satellite had a TV camera on board, and it was giving us a live telecast of global weather. Live telecasts are not new for us. We have a live telecast of Wimbledon matches or a football event. But putting a television camera on board a satellite, and as the satellite moves around or orbits around the Earth, it was sending a live telecast of global weather. But this TV camera on the satellite didn't last long because very soon afterward, the TV cameras on the TIROS satellite were replaced by scanners. Scanners these days are very common. I mean, you enter an office building, you're supposed to get your fingerprint scanned, or you buy something in the marketplace and there's a QR code which you scan with your mobile so that the bank releases payment. Or there's a document which you'd like to send somebody, you get it scanned on a scanner. But at the time of TIROS, scanners were new. And this was new technology which was brought in so that the Earth could be scanned from the satellite. So scanning the Earth meant that you run your scanner across the whole Earth from north to south and from east to west. And for every point that you digitally scan, you got a number. So basically what we got was an array of numbers. But people liked images. And so what was done was that the data was converted to an image. So for every point on Earth, which is scanned digitally by the satellite, we get a number. And for that number, we assign a gray shade starting from 0 to 255. 0 is black and 255 is white. So what results is that while previously we had a set of numbers, now we have an image. An image looks good. We like images because we want to put them on TV screens. We want to put them in a poster, or we can put it on the cover of a book. So the images are convenient. You can see them at a glance compared to data. What a satellite sees is something that a human eye cannot. That's why we need satellites. Like, for example, looking at a cloud, we look up to the sky and what we can see is the base of the cloud. But what a satellite, when it looks at the cloud, it looks from space and it sees the top of the cloud. So we have different perspectives of looking at the same thing. Like, for example, in the TV debate, there's a single problem and a lot of people arguing about it. And everybody sees that particular problem in a different light. In the same way, weather is seen in a different perspective from space and from ground. That's why we need satellites which see something differently. Visible light, as the human eye sees, is usually 7 colors. We see them in a rainbow, and we know the formula of Vibgyor: violet, indigo, blue, green, yellow, orange, red. But what a satellite measures, it measures radiation in different parts of the electromagnetic spectrum. So it can see wavelengths which are longer than red. It can also see wavelengths which are shorter than blue or violet. The spectrum of electromagnetic radiation was a subject that was taught in physics classrooms till recently, I should say. But now we use them every day. Like, you tune into an FM station, and what you're doing is you're using radio waves. You go into the kitchen to warm up your food. What you use is a microwave oven. You have a mobile in your pocket, it's microwave. You get TV channels from the dish, it's microwave. If you're having a problem with your knees, you can heat them up with infrared lamps. If you look at the rainbow, it's visible. Nowadays, sunscreens have become popular. You use them so that your skin doesn't get affected. If you go to a hospital, chances are that your foot may be x-rayed to find out the bones are intact. And if by any reason there is surgery to be done, the surgeon may use gamma rays, a gamma knife. So nowadays, the whole spectrum of electromagnetic radiation is something that we use all the time. Now, what a satellite measures is the same radiation in different parts of the spectrum. One is the window region, in which the atmosphere allows radiation to pass through. And the other is an absorption band, in which the gases absorb the radiation and do not allow the radiation to pass through. We come to the satellite orbits. There are different types of orbits in which a satellite can be placed. The most popular orbit is the polar orbit. The geostationary orbit is also equally popular. And the tropical orbit is something rarely used. So an orbit gives us a vantage point, a different vantage point from different places. We can see the weather and the Earth and have a look. The polar orbit crosses the equator twice a day. And in every orbit, every orbital revolution, it sees the polar view in every revolution. Now, besides that, the Earth is also rotating within the orbit. So eventually what happens is that we get a global picture over a period of time. The geostationary orbit is a special case that the satellite is launched at a height of 36,000 kilometers over the equator. At that height, what happens is that the rotation of the Earth matches the revolution of the satellite. So everything appears stationary to the satellite relative to the Earth, and we think the satellite is stationary. So we get a continuous Earth view from 60 degrees north to 60 degrees south, and the polar regions are not seen by geostationary satellite. So if you have 5 or 6 such satellites, you can see the whole globe except for the polar regions. With every satellite, there is a trade-off. There's nothing like a perfect satellite which gives you everything. You have to pick and choose between satellites or have many satellites if you want to have everything. Wavelength is the satellite payload which decides what you can see. Resolution, the sensitivity of the sensor will decide how clearly you can see. Ground coverage, the satellite altitude and orbit will decide how much area you can see. Repeativity, the satellite orbit decides how often you can see. So these are the things that you want to have, but you can't have them in one particular satellite because it's impossible to make a satellite with that kind of payload or to place it in an orbit which will give you all of those things. So every satellite launch or every satellite design is a compromise. If you just happen to look at a satellite image randomly, a single isolated image, the first thing you see, there are bright white spots. So we look at now how satellite images can be interpreted. Sometimes you see long bands of clouds, which are indicative of jet streams flowing in the atmosphere. Sometimes you may see spirals, which will tell you that there are tropical cyclones in the vicinity. You may have a look at the comma-shaped cloud, which are representative of the extratropical system. If you have multiple images taken at the same time but in different channels, we can find out what type of cloud it is. We can also estimate the height of the cloud. And we can also get an estimate of the moisture in the atmosphere. But if you have successive images over a long period of time in different channels, we can get the vertical development of local severe storms. And we can also monitor the horizontal movement of tropical cyclones, monsoon depressions, and western disturbances, which keep moving horizontally. For doing all these things, you need an imager. And an INSAT 3D imager has 6 channels. INSAT stands for the International Satellite, and 3 stands for the 3rd generation. And INSAT 3D has 6 channel imagers. One is the visible channel, one in the shortwave IR, one in the midwave IR, 2 in the thermal infrared, and 1 in the water vapor absorption band. The resolutions go from 1 kilometer in the visible to 8 kilometers in the water vapor channel. If you have a look at these channels at the same time, you'll get 3 different types of pictures. The one on the left is the visible channel image, almost like what we would see if we are sitting in the satellite and looking down. There's a yellow line across the Earth's disk, and it separates the sunlit part from the non-sunlit part. So a satellite in the visible channel can see anything which has sunlight available on that particular region. An infrared window image can make an image any time of the day. It doesn't depend on sunshine. It's basically a measure of the temperature. And the water vapor band image gives you moisture, the amount of moisture in the atmospheric column. This is also available 24 hours of the day. This is cut out from a full disk or a sector of INSAT 3D taken very recently, 10th of August this year at noon time, Indian Standard Time. And this is a visible sector. And you can see here that the oceans appear black because the ocean don't reflect solar radiation. And the land appears gray. And there are clouds which are kind of gray shaded, which are middle level clouds. And there are tall clouds which appear white. So this is what you will see in a visible channel sector. Same time, same date. If you take an infrared picture, something different happens. Now the hot areas appear black because the temperature comes in. The oceans appear gray, and some of the tallest clouds, they appear white. This is the third alternative, the water vapor channel image for the same time and same date. Here things are very different. The monsoon has set in, it is active, and you have moisture everywhere. So only in the northwestern region of South Asia, we have a blackish, grayish sector, where everything else is gray and white. There are 2 pictures here which are taken at the same time on 19th July afternoon. We have a visible image and an infrared image, and they look similar, but actually they're a bit different. Both are showing bright white spots because in the visible you have a reflecting cloud, and in the infrared you have a tall cloud. Both clouds, of course, are the same, and they all look visibly white in the image. So you can look at thunderstorms. Tropical cyclones, of course, are very easy to pick out in a satellite picture. The first one is Cyclone Biparjoy, which was over the Arabian Sea, 12th of June. This picture was taken, and it fizzled out or made a landfall on the Pakistan-India border. The other one is Cyclone Mocha of 13th May 2023, this year, on the Bay of Bengal, and it dissipated on the Bangladesh-Myanmar border. So this throws a pattern, and the moment you see a pattern in a satellite image, you can immediately say, look, this is a tropical cyclone. Now the pattern consists of a central dense overcast, which is white, the eye, which is grayish or blackish, and there are spiral bands. So this way we can identify systems in a particular pattern. This is a picture of winter fog, rather old picture, 2016 picture, inside 3D. This is in the visible channel. In the infrared channel, a fog cannot be noticed because the temperature is almost as good as the temperature of the Earth. But in the visible channel, the reflection is different. And we can see this fog stretching all the way along the foothills of the Himalayas from central northern India to Bangladesh. This is a picture of Himalayan snow, taken not by an Indian satellite, but by a US satellite, NASA Terra satellite with an instrument called MODIS. And the image was dated 20 November 2015. Snow is cold, and snow is also highly reflecting, so it appears white. So it's very easy to spot snow on a satellite picture. This is a series of 4 images taken in 2016 in January, 2nd, 3rd, 4th, and 5th. And you can see a comma-shaped cloud entering into the picture. This is an image of what is called a western disturbance, which these kind of disturbances, they kind of appear over the Mediterranean Sea first. And from there, they keep on traveling eastwards day to day over Iran, Iraq, Afghanistan, Pakistan, and finally into India and out of India. So you can see here that every day this system is progressing eastwards and bringing weather along with it to different parts of South Asia. This is a picture of the monsoon, not the recent one, but an older one, 2017. And the reason why I'm showing this is a water vapor channel picture taken on 18th of May. 18th of May is much before the cyclone advances into South Asia. But you can actually see from the water vapor channel the buildup of moisture ahead of the onset. And you can see the gray and white band stretching across the equatorial region, the intertropical convergence zone, and the blackish area, which is totally dry, where the monsoon is still far away. So in this way, there are various ways of interpreting satellite images. It needs experience and it needs a systematic study. But as I said in the beginning, that images are not made by a satellite, they're made by us. And basically, we have the data from which we make the images. So data itself can be used, and many products can be derived from the satellite data. First of all, it should be clear that visible and water vapor channels can be used only qualitatively because they are not calibrated. But an IR channel is calibrated with respect to the temperature, and we can derive basically 3 things: cloud top temperature, the sea surface temperature, and the temperature of the atmosphere. And you can see in this image, there are red isotherms which show minus 80 degrees Celsius, where cloud tops have reached, and there are blue ones which are minus 60, which are some of the lower clouds. Sea surface temperature is a rather straightforward application of satellite data. What we do is to use the Stephen-Boltzmann law and make an inverse application. And the temperature can be obtained from the radiance in the thermal infrared window reaching the satellite. So what these radiance gives us by an inversion is the skin SST, or the topmost surface of the ocean. But for getting this, you need a clear sky. Otherwise, you won't look at this ocean, you'll look at the cloud top. So there are attenuation and contamination errors caused by the intervening atmosphere and intervening clouds, and they have to be removed by using multi-channel algorithms. So there are problems, but in general, we can make a good use of the sea surface temperature across the world, because the only way to get sea surface temperature before satellites came was to use them from ships or from buoys. Now we have a global picture of the sea surface temperature. This particular map was taken on 9th of August this year. And you can see within the black boundary, El Nino developing on the coast of South America and stretching westwards towards the Indian Ocean. So we can, in fact, El Nino monitoring is basically with satellite data. When you look at the sky, you'll see clouds floating in the atmosphere. Some of them are randomly there, while some you can see that they're carried by the wind. The same principle is applied with satellites. You can, if you have a geostationary satellite with consecutive half-hourly images, you just pick up a cloud in a certain time image. Let's say it was at position A, and take a picture half an hour later, and try to figure out where that particular cloud has gone. Let's say it has gone to a place B. Measure the distance from A to B, divide by 30 minutes, which is the time between two satellite scans, and you get your wind. So it's almost something like we look at the sky ourselves and find out where the wind is blowing from. So these features are called tracers. They can be identified and tracked across successive images. So we can get a map like this. In this particular image, which was 17th of August this year, the monsoon was active. And there are these blue wind bars, which are upper level easterlies over the tropics. And there are the pinkish yellowish wind bars, which are upper level westerlies over the extratropics. Cloud motion winds are liable to severe errors because between half an hour, a cloud may change its shape, it may descend or ascend, and several clouds may look exactly alike, as happens when we look at the sky ourselves. So a lot of quality control is required to eliminate these kind of spurious winds. It's also difficult to assign a height to the cloud wind because we have to plot it on a synoptic chart, and we don't know exactly where it can be done. Outgoing long wave radiation is something which is very important because, as we know, our only source of energy is from the sun, and that has to be ultimately sent back by the atmosphere and the earth. If it is not sent back, we get global warming, and we know what's happening with that. So what we need to know is the outgoing long wave radiation, or the OLR. This actually is a broadband parameter. If you can see this blue band, it stretches from 4 microns to 80 microns, while what a satellite measures is in the narrow radiance range of 10 microns to 12 microns. So we try to estimate from the narrow band something which is in the broadband. Physically, it's not very correct, but statistically we can do that, and we're able to get OLR in watts per meter square for the entire global scene. This is a OLR map for 12th of July. And if you can see a little clearly, OLR less than 240 meters square, which is colored blue, is the monsoon area and the tropical area, which is convection, where convection is active. And the brown area is something like 300 to 320 watts per meter square, which are deserts or where there is hardly any convection. So what happens is we can, in fact, estimate precipitation, large-scale precipitation, from the OLR measurements. And OLR less than 240 watts per meter square, we can say, is a rainy region. And lower the OLR, higher the precipitation. This is an estimate. But actually, you can put an instrument on board and measure the precipitation from a satellite. Now, this is done in two ways. One is you can have a microwave channel radiometer, or you can measure it by an onboard radar. It's very easy to understand this because many times when we are watching a TV channel and it is raining somewhere, you get a message that the image is disturbed or missing because of rain. So a microwave radiation is affected very badly by rain. And if you measure the microwave radiation, we can actually compute the precipitation involved. This is a map of global precipitation for the month of July. July was a good month where it was raining quite a lot. And this is for the whole month. And this estimate is from what is called the Special Sector Microwave Imager. It's on a US satellite. The blue and green regions are the rainy areas. You can see that they are a little to the north of the equator, and the whole of South Asia is getting good rains. This was in July. There are many ways of measuring precipitation, not necessarily from the OLR or from other little instrument. There's an entire mission devoted to global precipitation measurement, which is called the GPM. This actually is a network of satellites. And there is one central satellite, which is made by United States and Japan together. And there are other partner countries which are providing a network. The main satellite was launched in 2014. It's still working at an altitude of 400 kilometers, and it covers the Earth from 65 north to 65 south. Now, this has two instruments. One is the GPM microwave imager, and the other is a dual frequency precipitation radar. What we get from this is maps like this. This was on 20th of July when the monsoon was active over South Asia. And you can see the red and brown spots, which are the maximum rainy areas. And the pink, of course, is a dry region. So we can get maps like these almost on a real-time basis from the GPM mission, covering, of course, 65 degrees north to south. But there is one rather complicated extraction of parameters, which is the vertical temperature and humidity soundings. I'm not going into details of this. I'm sure somebody else will be covering it later. But what happens is that whatever energy is received and absorbed by the ground has to be ultimately sent back. And if you can imagine that the atmosphere is made of several layers, every layer receives something from below and emits something above. Now, if you have a sounder, it's possible to find out by, again, an inverse process, how much of every layer has contributed to the radiance going to the satellite. And from that, by inverting things, we can get the temperature of each layer and its humidity. This is extremely important and useful because, as you know, radiosondes are balloon-borne instruments, and every time a balloon is sent up, the balloon bursts and the instrument falls down somewhere, it is lost. So radiosondes are expensive and they are inconvenient. Not only that, you can't put radiosondes over the ocean. So a satellite gives you what a radiosonde does on land, a satellite does for you over the oceans. So for this, INSAT 3D has a 19-channel sounder. All of them have a resolution of 10 kilometers. And there are 19 channels in different parts of the spectrum: shortwave IR, midwave IR, longwave IR, and the visible. So with all of these things, what really have satellites done to weather prediction? Well, they have several advantages. We know that very well. But the main advantage was that before satellites came into existence, everything was a long process which was done quite a lot manually. Data had to be collected, data had to be plotted on the chart, and the charts had to be analyzed by human beings, and so on. Now, when satellite pictures came in, you just got everything at a glance. You don't have to plot something or analyze something. You see the whole weather at a glance. And basically, areas which were not having conventional observation, that it was not possible to take observation, were all seen in that global image. But the main thing that has happened in recent years, which is a very significant advancement, is that assimilation of data into numerical weather prediction models now includes assimilation from satellite radiances. Radiances are not converted data, they are the data, original sources of data which reach the satellite. We don't derive anything from that. So these radiances, if they are assimilated into the models in real time, some of the errors which are going along with the satellite products are no longer involved. And this has made a significant advancement in the accuracy of numerical weather prediction models and their forecasts. So this, I'll say, is one of the important things that satellites have done to weather prediction. Right now, there are something like 16 geostationary satellites and 12 polar orbiting satellites orbiting around the world for meteorological application. Now, there is a Japanese satellite named Himawari. It's located at 140.7 degrees east. And if you see the full disk, South Asia is to the extreme west. It's in the yellow box. There's also a Chinese satellite, FY4B, which is at 123.5 degrees east. And if you see the yellow box, the South Asian region is in the northwest quadrant of this image. There is a Meteosat, which is a European satellite. It's called IODC, Indian Ocean Data Coverage. If you see this, South Asia is to the extreme east. But if you see INSAT, the International Satellite System, third generation, South Asia is ideally located in the center of the disk. There is no distortion of the map. There is no geographical distortion. And the images are uploaded to the IMD's website, mausam.imd.gov.in, and every half an hour, these images are uploaded. INSAT 3D is an operational satellite at 82 degrees east, and INSAT 3DR is a backup satellite at 74 degrees east. So one of the two are always available, and the images are uploaded to the website. We come to the fifth part of this talk, application to climate studies. As we saw at the beginning, that the first weather satellite was launched in 1960, almost 63 years since satellites started giving us data. So we now have a long series of archived satellite data from which we should be able to find out results about climate change. Now, this is a boon as well as a problem. The problem is this, that with every new satellite, the instruments have become better. The data is more accurate than before. It is covering regions which were not previously seen by certain satellites. So there are internal incompatibilities in a long series of satellite data, and you have to make adjustments to the accuracies and the resolution. It's not easy. In recent years, of course, many satellites are on par, but in the olden days of the satellite were not that much on par. So in spite of that, there have been several applications where satellites have been used, because again, everywhere satellites are the only source of information. So we have had two major projects. One was the ICCP, which was the International Satellite Cloud Climatology Project. The other was GPCP, the Global Precipitation Climatology Project, in which meteorological satellite data was used for getting a lot of information over the years. And we have averaged map, we have normals, we have seasonal, and things like that. But notwithstanding the meteorological satellites, there are at least 5 satellites which are meant specifically for climate studies. And there are 5 of them which I would like to name here. One is the OCO2, or the Orbiting Carbon Observatory. We have seen the Mauna Loa Hawaii maps of carbon dioxide, how CO2 has been increasing for the last 50 years, and they're very scary maps. But that is at a single point. While an orbiting carbon observatory gives us, it's a NASA satellite, it gives us the sources and sinks of CO2 all over the Earth. It's good to know where the CO2 is being absorbed and where it is being emitted. It's a nice source of information. Then we have a US-European jointly produced satellite called JASON-3. This is an altimeter. You know what an altimeter is? I mean, when you're flying on an aircraft, many times the pilot will announce, look, we are flying at 30,000 feet. How does he know that? Well, he has an altimeter on board. And similarly, an altimeter on a satellite will tell us where the sea level is, whether it is changing or it is increasing or what. And JASON-3 does it with an accuracy of 3 centimeters. It's an extremely accurate measurement. And there are 2 instruments which are used for ozone monitoring. They measure the ultraviolet and visible radiation. One is called the GOM-2, Global Ozone Monitoring Experiment. The other is ozone mapping and profiler suite. One is on a European satellite, METOP. The other is on a NOAA-20 US satellite. So they are giving us maps of ozone concentration in the atmosphere, particularly for finding out the ozone hole and its extent. OceanSat-3 is the 5th on this slide. It's an ISRO satellite, which is in operation. This has 3 instruments on board. One is for measurement of ocean color. The other is for measurement of surface wind over the ocean. And the third for the sea surface temperature. So these are some of the climate application satellites which are operational right now. But in future, and this is the last point in my talk, what does the future hold for us? That's the question. There are at least 4 new missions which are being planned for weather and climate, and I think we should know a little about it. So I have 4 slides for each of these bullets. TROPICS is an acronym for, it's not actually a geographical name, TROPICS, it's an acronym for time resolved observations of precipitation structure and storm intensity with a constellation of small satellites. This is an evolving program of NASA, and the object is to get soundings of tropical cyclones at hourly intervals. A small sat is really a small satellite, the size of which is 36 centimeters by 10 centimeters by 10 centimeters, and the weight is 5 kilograms. It's something like holding a small box in your hand. And you can imagine that the inclination is 30 degrees, the altitude is 550 degrees. It has a 12-channel passive microwave spectrometer, and it will give you a slice of a tropical cyclone at hourly intervals. So these are small satellites capable of doing big things. This is a program which will be coming in the near future. There's one more satellite called PACE. This is an acronym for Plankton, Aerosol, Cloud, Ocean Ecosystem. This is also a NASA mission. It's scheduled for launch in 2024, and it has an ocean color instrument. It has 2 multi-angle polarimeters, and it measures almost everything. It measures energy, water, nutrients, gases, aerosols, and pollutants. So this is something that's going to give us a lot of information on a lot of things. And in fact, aerosols are one quantity which cause a lot of uncertainty in climate modeling. So if you know more about aerosols, modeling will be surely better. Sentinel is a European satellite series to be launched next year onwards. That again is an altimeter. It has measurements of sea surface height, significant wave height, surface wind speed, and sea ice height and thickness. It has also got instruments for ocean color monitoring and for the sea surface temperature. The last in the series is a satellite called NISAR. NISAR stands for NASA ISRO Synthetic Aperture Radar. This is to be launched in January next year from Sriharikota, India. And it has 2 radars, an S-band and an L-band radar. And it will produce images of the Earth's surface with a resolution of 1 centimeters, a really fine resolution compared to all other satellites. And the application areas are many. It will see the melting of glaciers and ice masses. It will monitor the sea level rise. It will check groundwater levels. It will find out what's happening to ecosystems, forests, wetlands, and even get some inkling into the dynamics of earthquakes and volcanoes. This is almost my last satellite. It's interesting to know that in the last 5 months, almost 10 satellites have been launched to monitor weather and climate. It's good for us. And in the month of May this year, the US NASA launched 4 satellites in the tropics series, which will give us information on tropical cyclones. In April, China launched FY3G satellite, which is a GPM constellation member. It will give us information on precipitation. China also launched a satellite FY3F this August. It has an imager and a sounder. In June, Russia launched the Meteor M, which has an imager. And interestingly, private companies have launched 3 satellites. One is called Ghost 3. It has a hyperspectral imager. A satellite named Tomorrow. Tomorrow is the name of the satellite. It is measuring precipitation. And a satellite called Wokondor has a synthetic aperture radar. So these were launched, 10 of them in the last few months. So it indicates how much interest people have in this. This is my last slide, which says that the future is good. Satellites have become indispensable, as we have seen, for weather forecasting and climate study. We just can't do without them anymore. They give us global coverage. They give us information that no other source provides us. And good to know that most operational satellites have backups ready. So we will not be lost if a satellite is lost. And several new missions are coming up. So there is a great potential for the use of satellite data for the South Asian region for reasons that we are not able to monitor the whole of this region by conventional observations. And satellites are something which fill the gap. And at the beginning of this session, Dr. Tyagi mentioned that satellite meteorology has to be given more importance. He said that, and I say that again, that after climate change and numerical weather modeling, satellite meteorology has been rather given a backseat. It needs to be pulled to the front row again. So with that little comment, I complete my talk. And thank you for listening to me, and also my best wishes to people in South Asia. And they have a choice of satellite. They have a lot of information available online, and they can certainly use it. Thank you very much.
Thanks a lot, sir. I mean, it's really, satellite is indispensable for coming weather forecasting. Just giving one example, in 1999, when that cyclone was happened, that whole Odisha was, massacre on that time. I was student. I asked actually that time meteorology.